Hello and welcome to T-Tricks. Today we're going to be working on Lewis dot diagrams. And in reality it's the bonding theories, but you mainly just use them to write Lewis dot diagrams. Right, so this is what part's going to go on. So essentially, in order to understand how to draw a Lewis dot diagram, you need to know three things about bonding theories, and that's the molecular geometry of like the molecule or compound, the electron geometry, and then the permanent dipole moment. Now, the permanent dipole moment is just whether or not the compound is polar, and if it is polar, there is a permanent dipole moment, and if it's not, then there is none. So let's take water for example. So here we have water, H2O, write it like that. Now water, if we write it out on a Lewis dot diagram, or at least just like without any proper electrons or whatever, if you just like wrote it out, you would expect it to look like that, right? So if we have like electron bonds at each of these two lines here, then we'd essentially, let me pull my frog out. Can you guys see the frog? Oh, you guys can't see the frog. All right, he's gonna go like right over here. All right, frog is out. Very important that he's here. All right, so if you look at the two bonding points, normally in like a covalent bond, for example, those two bonding points would be like shared. Whatever. However, oxygen is very electronegative. In fact, it is the second most electronegative element on the periodic table from what I understand. So that means that hydrogen, being the least, is very unlikely to actually be able to like keep the electrons in this bonding point. So we look at it a little bit better here. This here shows the shared electrons. Shared electrons, and because of oxygen's electronegativity, most of the time the electrons are going to be on this side near the oxygen instead of being by the hydrogen, which makes hydrogen normally positive in H2O and water normally negative. However, they are still covalent, so occasionally hydrogen will have electrons, but it's very unlikely. So that's polar dipole moments. Let me get water out of the way. Also, by the way, this drawing right here, that's not accurate. If you're drawing a Lewis dot diagram like that, don't do that. That's not the correct. It's almost correct, but don't write it like that. All right, so let's get to molecular geometry and electron geometry. So essentially they're very similar, but the difference is what they are referring to essentially. And molecular geometry refers to, so the difference between them is that molecular geometry is related to the central atom, while electron geometry is related to the electron pairs around the central atom. So if we look back at water, actually, let's have our fake water diagram. Essentially, the molecular geometry of water would be referring to how these hydrogens are placed based off of this oxygen here. It's like how they're placed. So assuming we'd had electron geometry over here, that would be referring to how these bonds are shaped, like where they're kind of shaped. So if we had a more complex diagram, or if I had a 3D diagram, which I might pull up in editing, you'd understand like the difference there. But essentially, it kind of changes based off of like the 2D image that we have here and the 3D image we have here. And because of the fact that Lewis dot diagrams don't actually represent molecular geometry or electron geometry, because we have a 2D image, and last time I checked, we don't live on paper, so our world is not 2D. So you can't really properly show how a diagram should look in 3D on paper. So that kind of sucks. But anyway, so now to actually drawing Lewis dot diagrams. So in order to draw one, you gotta know the valence, the valenceness, like the valence electrons of the central atom and the atoms within it. So let's take this example here. We'll do arsenic iodide. So arsenic iodide. So you should know that arsenic iodide is AsI3. If you don't, that's just based off of the periodic table. And also the fact that arsenic has a charge of positive 3. Iodide has a charge of -1. So that's got to be 3 iodides to equal that out. So you have 3 instead of -1. So anyway, putting that away. Okay. Arsenic iodide. So what this should tell you is that there's supposed to be 3 iodides somewhere and 1 arsenic. And essentially the first molecule, most of the time, is going to be the middle molecule. But the best way to really show it is just the singular molecule is going to be the middle molecule. If you look at our example of H2O, obviously oxygen is the middle molecule, is the central atom, and hydrogen is the outer atoms. So if we write this, we'd have an arsenic in the middle, and then we'll put some iodides to the sides. So if you realize where arsenic is on the periodic table, which I believe is group 15, and iodide, which is in group 17, you can actually use a little trick with that the groups from 13 to 18, I believe, show the actual amount of valence electrons that you're going to need, or that they have. So essentially, if you look at arsenic, it's in group 15. It's going to have 5 valence electrons. If you look at helium, which is in group 18, or let's use iodide because it's actually there. So if you look at iodide, it's in group 17, so it's going to have 7 valence electrons. So we need to show these valence electrons somehow. So how do we actually show them? We just use dots. So we're gonna draw some dots over to the side. So essentially, if we have iodide, there's supposed to be 7 dots around it. So we have 1, 2, 3, 4, 5, 6, and 7. You can't just have this electron like by itself. That's essentially why we have the issue that iodide actually pairs with arsenic. So in order to have this connect or whatever, we use these bonds right here. And one of these bonds, so if I get rid of the iodide single lone electron, we have a line here. And that shows that both iodide and whatever's over here has an electron. I'll just do atom. So both of these share 1 lone electron. So if we go back here, we have 1, 2, 3, 4, 5, 6, and this is going to be our 7th. We'll do that for all of the iodides. And then arsenic already has 3, since there's 3 lone electrons that it has, and then it has 2 more left, so we're just going to write that at the top of the arsenic right there. And that's arsenic iodide on a Lewis dot Lewis dot diagram. Now, we also have to mention the molecular electron and the what's it called? Permanent dipole moment. So, essentially, I'll show a chart in editing, but there's really just like not necessarily an exact way to know it. Kind of just memorize it. There might actually be a way to memorize or to know the molecular and electron, but I don't. I was just using the chart. So arsenic iodide has a trigonal bipyramidal. Let's not spell that wrong. Pyramidal. That's the electron geometry, and then it's linear for its molecular geometry. So if you were to look at arsenic iodide on like a 3D scale, it would essentially be shaped a little bit more like trigonally, I guess you could say, on a actual level, like 3D level. But of course the Lewis dot diagram doesn't actually show that. And then finally, for the permanent dipole moment, arsenic iodide is in fact a covalent bond, which means that yes, it does in fact have a permanent dipole moment. And to memorize or to understand the covalence, there is a value that you can use. So let me just erase some of this. I'm gonna get rid of arsenic iodide. So non-polar, well, first off, if you know the electron charges or whatever, the electronegativity charges, a non-polar value is going to be 0. So essentially, let's say we have a like negative 1.7, and then just 1.7, that's going to be 0. So then anything greater than that in a certain range is going to be a polar covalent bond. And then anything up to 1.7 is going to be, anything greater than that is just going to be an ionic bond. Ionic is just the case in which an electron is completely stolen instead of just being shared. So that value can, or this graph here can kind of show you that. And then that's pretty much it, actually. That's everything that you need to know about Lewis dot diagrams, bonding theories, really. And there's a little bit more, but specifically for this part, there's not much. And really quickly though, if we go back to arsenic iodide, we can talk about lowercase delta and what that means. Oh, well, no, it kind of sucks that I got rid of all that. I'll just not redraw all the dots. But since arsenic is taking the electrons from each of these iodides most of the time, arsenic is oh wait, no. It's actually vice versa, I believe. I have some mark on my desk. I'm not actually sure which way is the case, but let's assume that arsenic is taking electrons from iodide. You'd write lowercase delta, that's a little lowercase delta for you, and then you'd write that as negative. And you write that these are positive since they are most of the time not having the electron. So that lowercase delta is kind of a way to show that it's not a permanent replacement or like loss of electrons or gain of electrons, but it is most of the time going to be the case. And then that is in fact it. And if this is wrong, correct me in the comments. I apologize. Just wanted to add that in really quickly. And have a good day.